Hello everyone, I am Vipul. Along with my teammates, we are going to present research paper on the topic transferable representation learning with deep adaptation network. Today we are going to present deep adaptation network which are used in domain adaptation. The main problem is that the deep network loses uh, feature transferability in the higher specific task layer due to increasing domain discrepancy between the source distribution and target distribution. So to solve this research paper propose deep adaptation network, which basically transform the task specific feature into spatial space called reproducing kernel Hilbert space and minimizes the difference between the distribution using multi-kernel MMD. This formulate as mean max optimization problem. It also uses unlabeled target dataset, multi-kernel learning, adversarial test location. As a result, it achieves the state-of-the-art performance on dataset like Office 31, and the data settings are here we have source domain DS, the labeled sample from distribution P, and target domain DT, which is basically the unlabeled sample from distribution Q. Here P is not equal to Q. The total labeled data set is basically NA is equals to NS plus NL. Unlabeled target data is NU is equals to NT plus NL. So this the issue is the data shift layers becomes star specific and don't transfer well. So what Dan achieves? So Dan reduces the domain difference by transforming features into RKHS, which is basically reproducing kernel Hilbert space and minimizing MMD across the layers. It also adjusts distribution boundaries using entropy minimization and provides theoretical guarantee that RTF is less than RSF plus MKDS, which is basically the dot product of DN and DT plus CL. So reducing MMD removes target performance. So the core concept of reproducing kernel Hilbert space. So now we'll understand the kernel functions. So here, as we have written, kernel function is nothing but the inner product of x and x dash. The key equation is f of x equals to the inner product of f and k, x and x dash in the Hilbert space. So this means the value of the function f of x can be computed as the inner product with the kernel function. So next we define f of x, phi of x as k x x dash. So this defines a feature map mapping inputs to the higher dimensional space. So the kernel inner product in that space gives us the kernel trick. We avoid computing higher dimensional features explicitly. Kernel mean embedding. So now we represent a distribution as a point. So this means we all take the samples, map them, and average if the kernel is good. If kernel is good, P is equals to Q, means the mean of K, P, and mu of mu K, P, and mu K, Q are equal. So the distribution are equal if the embeddings are equal. So the kernel mean embedding is basically we represent a distribution as a point. So this means we take all the samples, map them, and average. If kernel is good, P is equals to Q. So mu K P and mu K Q are equal. So the distribution are equal if embeddings are equal. Also, the expectation of f of x is basically the inner product of f and mu K P. So the expectation becomes the inner product. So MMD, basically the maximum mean discrepancy, measures distance between the distribution MKP and MKQ. So in the expanded form, it can be written as EQ, which is norm of mu KP minus mu KQ. And we are then we'll take the kernel of x and x dash. Then we'll add the expectation of kernel of z and z dash, and we'll subtract the two x dash, the kernel of x and x dash. So we use only kernel values. If MKPQ is 0, then P is also equals to 0. So empirical version is written over here. So this computer distance using sample, but it costs O of n square. So deep adaptation network uses faster methods. Now we'll see the deep adaptation network architecture. So deep adaptation network architecture uses networks like AlexNet with layers. So from layer 1 to 5, it's the feature layer, and from 6 to 8, it's the task specific. So forward pass can be written as equation HL forward class can be written as this: L for xi, and W, L, and BL are the weights, and A to the power L is the activation. So Dan applies MMD on higher layers like F6 and F7. So lower layers fine tune, higher layers adapt using MMD. This aligns source and target features. Now Himadri will take over.
Now that we understand the multi-layer architecture, let's look at how Dan actually measures the domain discrepancy. For this, we use multi-kernel maximum mean discrepancy. Why we use multiple kernels? Because a single Gaussian kernel with a fixed bandwidth only characterizes the data distribution at a single scale. If we want a robust alignment, we need to match various statistical moments together. To achieve this, Dan uses a convex kernel family. Okay, as you can see in the equation, this is a linear combination of m such kernels where the weights are beta and they add up to 1, and the bandwidths are sigma, are generated exponentially around a base median value. By learning the optimal combination of these betas, which act like a different statistical lenses, the model can capture the complex structures of deep models across multiple scales. But there is a computational bottleneck here, that for using the MMD estimator, it compares pairwise distances between all source and target levels samples. This order of n squared complexity is very computationally heavy. So to solve this, the authors introduce a linear time unbiased estimator. They group the data into quadtuples, that is two consecutive samples from the source and two consecutive samples from the target data, and calculate the kernel difference dk exclusively within this within this quadruple of 4 samples. By summing these independent differences, the computational cost drops to the order of O of n, and more importantly, it fits into the batch stochastic gradient descent algorithm that helps in the update of the web efficiently. And we have another alternative to the MKMMD test. As we saw that MKMMD compares the global average distance within the distribution. ME test is highly localized and interpretable. It learns a specific set of J test locations denoted by V within the Hilbert space, and it calculates the differences using the Hotelling T-square statistic, the second equation in this slide, to measure the difference in these test locations only, denoted by Vj. As we will see shortly, these test locations are not static. They act as adversarial probes that actively move to the regions where the two domains differ the most. But even if we use the MKMMD and ME tests perfectly against the two domains, but still we will face a problem. The classifier decision boundary is learned entirely from the source levels. This boundary might accidentally pass straight through a dense cluster of unlabeled target data, leading to highly uncertain predictions. To correct this, Dan incorporates entropy minimization. We calculate the Shannon entropy of the class probability outputs of the C classes on the softmax outputs of the unlabeled target data. By mathematically forcing the network to minimize the entropy, we are essentially demanding that the network makes highly confident predictions. This principle, known as the low density separation, acts perfectly in tandem with our kernel alignment. Next, we put all these three terms into a single equation for this paper. First, the standard cross entropy loss to maintain the classification accuracy on our labeled data. Second, the entropy penalty on the unlabeled target data scaled by gamma, and our multi-layer MK or MKMMD or ME loss scaled by lambda. The optimization at the very beginning of the equation uses minimization over F and maximization over the kernel family K. This represents the fundamental shift in how the network trains. The entire DAN network operates as a adversarial minimax scheme where the deep network, it tries to minimize the overall objective function, including these three. It learns to make the source and target distributions to overlap, trying to make them indistinguishable while maintaining high accuracy. Whereas, on the other hand, the statistical test, either the kernel weights in NKMMD or the test locations in the ME test, its goal is to maximize the exact same test statistic. It acts as an active adversary, continuously shifting its parameters or kernels to hunt for any subtle hidden difference between the domains that the network might have missed. By forcing the network to compete against a continuously improving network, it cannot rely on mathematical shortcuts. It is forced to learn genuinely domain invariant representations. In the next slides, we will learn how we actually compute the gradients using that protocol.
So we have now assembled the full DAN objective function. The question is how we actually differentiate through it. So how do the gradients plot when the part of your loss is a convex function related to the neural network? So we have the here the loss function is the combinations of actually the combinations of the gradient is dependent. The mini batch gradient is dependent on three terms. The first term is that the first term is actually the cross entropy gradient back projected through the labeled batch that is denoted by the BA and the second term is the entropy gradient flowing only from the unlabeled unlabeled data sample that is denoted by the B of U, and the third term is the MMD kernel gradient, and this is this flow from the paired source target tuples through the kernel functions all the way back into the weight matrices. And here there is a gamma and a lambda. These are the hyperparameters which can be tuned tuned by ourselves by we can tune also by the implementing of the fine tuning. And the batch B samples we have created is the combination is a union of available data set and the unlabeled data sets. So unlabeled data sets, we have the labeled data sets in the sum of the source data sets, and so these that be the batch created with the combinations of the available and unlabeled data sets. Then if we look at the equations number 2, the equations the first we differentiate the kernel. First we differentiate the kernel evaluated between the source activation, that is the H of SL and the target activations. This one is HJ TL. L is for the layer and T is for the target source, and J is J. We are going through the each and every locations for the part of things. So the feature before the ReLU first multiplied by the if we perform the actual differentiation with respect to WL. So by the chain rule we can write is equal to del of K of HISL HJ TL with respect to the del of H of SL H of SL, and then del of H of SL with respect to the del WL. Then we have the H of SL function is the combinations of the H of L activations layer AL into H of SL into H of SL minus 1 and WL, that is a weight plus bias with respect to the layer. So then after that we differentiating with we get this stuff with respect to the weight. Then when we get this after that things then we will go for the equations number this is the equation number 13. So we get it with respect to the again we are trying to the source level, and that is the H tilde. H tilde is just a representation. So like the H tilde can be represented if we know the H tilde is represented by like it's just a combinations of WHL HSL minus into BL and into BL, and where the HSL is the combination of activations, but activations layer is be the product of the H of SL L minus 1 minus plus B of L, sorry, minus plus B of L. So this is the functionality we used for the training the gradient. Then again, then the next slide. So these are these two equations. This is the back propagate through actually this is the with weight vectors and this is source layer predictions, source layer outputs. So when we go in the next slide is the emit rest gradient. This is the so then when we switch from the MKMMD to the mean embedding system, a new sort of learnable parameters enters in the picture. There the test location is the combination of divided by the V is the combinations of V and V and V2, V2, Z. These are not fixed. They are the learn level. Learned by the gradient ascent. So this is the equations. This is the equations. These equations describe this equation defines the gradient of the AMI test as static with respect to the single test location. Test location so that is the VJ that we are denoting here VJ. So the if we differentiate that thing, so if we differentiate the so we will get it like the outer factor is the mean differentiation of the kernel evaluations for each sample and the kernel between the kernel between the source feature HSL and the test location VJ minus minus the kernel between the target feature HTL and VJ. This is the measure how differently the test locations see source versus target. When this quantity is large, so the test locations is the discriminative in the region. The inner factor is the gradient of those. Inner factor is the gradient of those the kernel evaluation with respect to the VJ itself. Again, a weighted sum over m kernel multiple kernels, each contributing a full proportion to the K of U. K of U is the K of U and directed along the difference vector H of SL minus of VJ and H of STL minus VJ respectively. The product of these two tells the test locations move in the direction that increase your ability to distinguish source from the target. So these test locations are operated by the gradients to maximize the MEA statistics, the network weights, and are uploaded by the gradient descents. Each player is solving it. Each term and each frequency the term of the player is solving the half of the minimax problem, and they try to reach the find the Nash equilibrium situations. So the pipeline works like with the combinations of these equations. We can say that with the gradient descendant and this MMD, the ME test gradient. The pipelines work like we created like a mini batch. Then we compute the MMD. After the compute the MMD, we apply the back propagations, and after the back propagations, the network will get updated, and then updated network also updated the kernel beta equation, which we see in the later in these sections. In these sections, how the kernel is getting updated, and then after the getting the kernel updated, so then this comes actually. Then we update the locations according to which locations is make more distinguishable distributions. And this works in the cycle. So everything when the new locations comes, then that will be on that will be the mini batch will be computed, in mini batch will be created, and then the NMD will be created. Then these all things follow in the way. And then this part is the one of the part that is ultimately in the entire paper. So in the entire thing, so we are doing the main theory. We are optimizing main three factors. One is the network feature, network parameter FL, and the second is the kernel weight beta on which the kernels are getting updated. And the third one is the test locations that we have seen in this equations number 14. So after that, so this method is actually so the MKMD information is an immediate. So given M credit, how do we choose the weight beta? Actually, this is the beta is we have written in the linear combinations of the beta into K of U kernels of U. So how the beta can be chosen for the better optimal kernel. So for optimal test power, we want to kernel mixture that is the one most likely to correctly reject or null hypothesis target come from the same destination distributions. So when we look at these functions, so be the x square is the variance of EIQ, the covariance matrix, the written in the form of this the covariance factor, the covariance matrix Q encode the statistical dependency between the different kernel evaluations, evaluations. So this also the compute is the high computation. So if it comes like of omega of O of m square n time for the particle special problem. And so this is minimizations of the minimizations with respect to the minimization with respect to the minimization function is equal to beta transpose in the Q of epsilon into I. So here m is the vector of the pre-kernel, the pre-kernel MMD values, and the constant m transpose beta is equal to 1. Normalize the singles and the small dimensional relations. That is epsilon is going to be very smaller value. Ensure that the problem is strictly convex, numerically stable. Numerically stable. So in this way, we can by using this, we can what I can so we can optimize the kernel selections. After the kernel selections, then everything we have done by the creating by extracting the features, then applying the MMD. After applying the MMD, we have created the loss functions. After applying the loss functions, we have applied the gradient descent and how the backpropagations happen. After doing these all things, then how we will test that after that our DAN functions is actually is working fine on it, is working and fine on it. So for this, there is a theorem given by Van David. So that is that that theorem is like a risk factor with respect to f is should be smaller than risk factor with respect to the source of f plus del of h p with respect to the p and q. These are the distributions plus c some constant. Is considering the reducible. This is the some constant usually we can say it. So this is the central theory, the result of the paper. It says that the target risk is controlled directly by the MMD between source and the target features, source and target features. Reduce the MMD and your probably tighten the target risk bound. Now connect this back to the minimax game, minimizing the MT over the T. The network is objective minimizing MK over the kernel K gives the most conservative, most discriminative version of the bound. The worst case, kernel finds the longest possible domain gap, making the guaranteed millisecond rather than the vacuous. The minimax formulation is not an algorithm conveyance. It is the formal installation of this theoretical requirement, but both the gradient descent and descent direction is created by the by bound. And so after that, then this is the conclusion insight. So we have gone through that how this conclusion is concluding. It's like and then how we are able to make that by using the MMD by distributions matching and AMI tester and the gradient descendants. How can we make in the DAN make the feature transfer from one domain to another domain without actually decreasing the performance of the transforming the one feature from the one domain to the another domain. So these are the sums exactly that. So MMD minimization is a global operation. It matches the marginal distributions as I discussed in the earlier in the previous slide.